a new chapter, electric machines. So you might ask what we did before. It was not electric machines, it was electric machines. Electric machines in general, if you look at the types, you have static machines and you have dynamic machines. They're static machines, transformers, no moving parts. It's just static. And for the dynamic machines, we got two. Can operate as a generator or more. So in the dynamic electric machine, have one input and one output. If the input is electrical, supplying the machine with current, voltage, and the output mechanical energy, which is torque and speed, so that's motor. That's the motor. But if you are supplying the machine with hitting the shaft by line or anything like that, and producing electrical energy, so you are operating with the generator. So actually, any machine can be operate machine or generator, both. And the one responsible for converting the electric system, vice versa, it's the coupling field, the field inside any machine. So what type of dynamic machines, electric machines that we have? We have DC machines, AC machines, and special motors. The DC machine that we're going to start today, and they have many types. I'm not going to mention the types now, just DC machine, motor or generator, and then AC machines. And AC machine, they have two main categories: induction machine and synchronous machine. Induction machine usually used as motor in industry. It's like the horsepower of the industry, but recently have been using as a generator in wind energy. Synchronous machine synchronous machines have been used for a long time as a generator, alternator, especially in power station, big alternator. And there are different types used as motor, and we're going to talk about, like there are small synchronous motor used in watches, and there are linear motors used in like the speedy train, the bullet train. We're going to talk about it also in the end, toward the end of the semester. And then we have the special motors like stepper motor. Stepper motors usually used with robots when you want to, or the gripper of the motor, the little things. And brushless DC motor, that's kind of a synchronous motor, but using control system to make it operate as a DC motor. But the difference between the conventional DC motor we're going to study, we're going to start this lecture, has brushes. But this brushless DC motor, it's synchronous AC, but by control we can get the DC performance, the DC characteristic in this machine, and use now recently in EV, electric vehicle, because of many advances we're going to talk about it. There are hysteresis motor, reluctance motor, universal motor that can work as DC and AC. So these are the type that general, the dynamic electric machines. But we're going to focus in this class on DC machine, induction machine, synchronous machine. And if there's extra time, we can take another special mode. But I prefer to add linear synchronous motor, because it's very important that used in the high-speed train that used in Japan and Germany. So before we start any machine, we got to review quickly. We did that already, but we'll make fast revision about the principles used with electric machines. In electric machines, either motor or generator, there are two main laws that control the operation of these machines: how to produce induced EMF and how to produce force or motion. And even if the machine operating as a motor, there is induced EMF, and also there is force produced by the magnetic field. So how the electromagnetic force F, if you look at that, how it's produced, you have a conductor, and this conductor, there is current flowing in this direction as shown, figure, and then you got flux density or magnetic field directed from the north to the south pole. So there is interaction between the electric current and the magnetic field. It will cause the conductor to move. And that's the formula used for calculating the force. It depends on the flux density B, L, the length of the conductor, I, the amount of current or amps in this conductor. So that's the magnitude. About the direction. The direction is, as I show here in this simple rule, using the right hand, if I'm going to do the same. If this is the current, this is the vector of the current, so in this direction, that's the current. And no, that's the current. Another way I can do it, and see what you find. How you calculate, how you find the direction of the force. So as you see here, that the conductor will be lifted up. So that's the force. What about the, that's all, I know we did that in physics, but I like, just make it fast so you'll understand what we're doing here. Then the second thing, producing induced EMF, we call it motional voltage caused by motion. And it's moving now. So this, because usually you have something moving in magnetic field, then you produce voltage. And the flux density, there are x's, is going in. So I try to do it. In this direction, and there is flux coming to my side in this way. So this is the direction of the conductor. I am the conductor, right? Yes, upward. And that's the velocity, direction of motion. And that's the flux going in like that. You do the same thing. The other time when you calculate, when you try to find the direction of the motion of the force, you move the have V, that's the variable V. You move V towards B and C is going up or down. Direction of motion, the velocity V. So imagine you're doing like that. So what's happening? It's going upward. So the current will flow upward in this thing. So if you have this is closed circuit, so the current will be flowing in this direction. And I showed you here how you can do the thing by your hand. That's the velocity, and that's the B. So move your hand, curl it to put it first in the direction of the velocity, and then curl it toward B, and see where is the thumb. Up means the current will go up. So that's how we calculate the direction. About the magnitude of the voltage, it depends on the flux density, the length of the conductor, and the velocity. So what is different between both formula? Flux density affecting both, the length of the conductor affecting both, but there is one has a current, reduced force. This one is moving, velocity, you have EMF. Simply, right? Without going through a lot of math or vector. Now we'll start for the basic structure of any electric machine. Any electric machine, when I'm talking about electric machines, I mean the dynamic machines. I'm not going to mention the word dynamic anymore. Electric machines generally has two main parts. Maybe they have extra parts, but the main two parts, they are two: stator and rotor. Stator, the one that's fixed, does not move. And when you look at it here, where is the stator? That's the outer surface, that's the stator. That's contain everything, not only protection, no. Also, the stator, sometimes they have the magnets to produce a magnetic field. Maybe permanent magnet, maybe winding, and there's current in it to produce magnetic field. So that's the function of the stator in most machines. But they are fixed, stationary, they do not move. And then you have the second part, rotor. And by the way, this machine, it's AC machine, it's induction machine that's used a lot in industry. So they have the rotor, this is the moving part. And it's coupled with the shaft, and there are bearings, mechanical things was moving to minimize the friction, and also has winding. And usually the windings or the wire inside this rotor, both in some slots, they call it armature, right? So the one in the stator, if it's producing field, call it field winding. And if it just carry the current, like in the rotor, we call it armature winding. So winding does not produce the magnetic field. The other one, the field winding, produces magnetic field. And there are extra other parts, small parts, bearing, mechanical thing, but I'm focusing about the main two things, rotor and stator. Now we'll go for our machine that will start today, the DC machine. It has also the stator and the rotor, but let's get just a little bit in detail. I'm not going to talk about the mechanical parts, bearing and shaft like that, but I'm going to talk about the stator and the rotor, especially the rotor. The rotor of DC machine and others, it has commutator and brushes. What does it mean, commutator? That's the commutator and brushes. They are not in the stator, of course. They are assembled on the rotor. So that's the rotor. When you look at the rotor, that's the rotor. By the way, that's the stator, and you can see here the field winding. I can tell that this machine has 4 poles. You have, that's one, and let's just, and that's the second, the third, the fourth. And usually they take care of the direction of the current. So if they make this north pole, the opposite one, they make it north, and that's south, that's south. So you have north, south, north, south. That's 4-pole machine. There are 2-pole machine, 4-pole machine. You can have more, but 4 poles, they are common, used in industry. 2 poles, in the toys and things like that, a small size. Because when you have more poles, you have more magnetic field, they are powerful. So that's the stator, as you see. It's just the whole function of this, not the only function. The main function of the stator is to have the field winding to produce the magnetic field. And we're going also in detail about the poles, how they look like exactly inside. But that's as you see here. And supplied by DC, by the way, not AC. So once you have the North Pole, the South Pole, they stay all the time north and south. that will be different than AC machine when we study, when we have alternating current will be from positive to negative, so the poles will be changing. But now we have, once you have DC applied to the field winding, then you will have north, south, they never change. Well, about the rotor here, the conductor, that's the conductor. You see that conductor, there are some kind of slots there in the rotor and laminated. And I'm going to show you a bigger picture of it also. And then the winding going through this one. And then they go through, let me just follow one here. That's winding. And then it will go there. And here the commutator, it's commutator like made of copper, small piece. Like a ring, as you see here. So every single segment connected to some bundle of wires. So the current can go through the wires. Because if you operate this as motor, so you want the current come from the battery and then go through the commutator, and the commutator connected to the wire with the coils, and then the current goes to the coils. So commutator is like the way to transfer the DC current to. But the problem is how to connect the commutator to the battery DC source. How you do that? If you connect wire to the commutator, it will be big mass, right? Imagine if you weld, let's say that you weld here wire to go to the battery. So when it rotate, what will happen? The whole wire will go, right? Why don't you wash your face and just look up? No. You look tired. No, one behind. Yeah. You're tired? Okay. So that's the commutator. So how you solve this problem? To solve this problem, let me just jump to another slide to show you what happened exactly. They have a picture for it. Yes. That's how we solve it. That's a very simple commutator. It's only 2 pieces, but you have 100 pieces. That's the commutator, just like 2 split pieces of conductor, and the brush is just touching the commutator. And there's kind of maybe when I was students said, oh, how the brushes will be hanging in the air like that. So I got to look at the machine by myself. I look at the machine myself. So let me just solve for you this thing. That's the stator, right? So what's happened that this one, there is a spring connect. I saw with my eye that there is a spring connected the stator to the brushes. So it's like breast. So when it go and touch the commutator, it will be really in good contact with the commutator. So, and that spring is isolated from the brushes. They are made of carbon, by the way, made of carbon. So the wires will come from the brushes here to the battery, one to the positive, one to the negative. And this commutator rotating all the time. So when it's rotating, but since the carbon connected here to this brush, let's call brush. This brush connect to the positive, this brush connect to the negative. So all the time, the current will be flowing from the positive to this one. This commutator is rotating. So this part is positive and this one is negative. So supplying the current to the coil, and then it would rotate. This negative come to the other brushes, other brush, so it will get the positive. So when the coil rotating, so all the side will go, the current will go in from the positive polarity of the battery, and that's the way they suspend the brushes to the stator. So always pressing on the commutator to make good contact with it. So. Benefit you in calculation equation, but just as like when I was sitting, I would like to sit down just a minute, say brushes, and then the professor said brushes. I said, okay, they are hanging in here. What? They didn't say anything, just, but I got to look at it. Yeah. I'm not an easy believer, you know. I have to see by my eye. Okay, so we did for the DC mode in general. So it has brushes, and the brushes, it's a problem of the DC mode. That's why you thought about brushless DC motor. You have big advantage. We're going to when we talk about the characteristic of DC motor, you will see really they have good characteristic. They have like 3 types. They are really good, but the only problem, brushes. Then you will ask, what's the problem with the brushes? When they use it previously in the vehicle or cars. I remember my car has this. They use it to start the engine. When you start your engine, you have internal combustion engine. So the internal combustion engine, they cannot start by itself. It has first something to move it, and then after to move it, it will start burning the gas, and then the compression, all the cycle that you know. But just needed the beginning. So if you watch the old movies, have the cars in the beginning, they didn't have this DC motor. So they have something like I don't know if you see it or you didn't see it, something like that. Then they put it inside the auto. Let me just, I'm going to show you. I like these movies too. Okay. Yeah, it's really, you know, remember this old car, the huge one. You have huge car. Yeah, here you go. Okay. Then they have here in the front kind of a place here. They put this tool, right? If you watch Charlie Chaplin movies before they have the whole, and then just yeah, is starting the engine. The internal combustion engine has first to move to start the process, and after that, it's once the cylinder starts moving inside and burning, that's it. They start, but it has to start somebody to push it. So they do that. So after they did the DC motor, so they have DC motor inside, and you have the ignition. That when you do that, you're operating DC motor to move these parts until the combustion engine start. It just starts for half a minute, and after that, that's gone. And that's it. That's what's happening. The problem is that these brushes, there are sparks. Because when the commutator, let's go back to the. So see the brushes here in contact with the commutator. Yeah. Yes, they are touching rings. So when it's rotating, it's kind of oscillated a little bit. And that will make like space. That's number one. And even imagine when this commutator moving, there is a space between these 2 halves of the commutator. Of course, also, it cannot be like hanging in air to it, right? It's like there's a cylinder, insulated material, insulation, and then they put the piece of metals around it. So it's already on a frame of a shaft made of insulated material, but the space between the 2 halves is insulation material. There is no conduction. So what happened when it's moving like that? There is a space that the brushes not touching the metal or between the 2 metals. So it happened high voltage change on the commutator, which causes sparks. I saw the sparks. I open and I look at the cards here. I saw the spark. So this sparks cause deterioration in the brushes itself. So you'll find deterioration in the brushes. So you can have the new brushes like that, and then after a while, find it just start to deteriorate it. So you got to replace it. So it needs maintenance. That's why they use a lot induction motor in industry, because they have brushes and they work in any environment, dusty, anything like that. But these motors are delicate and heavier too. So that's the problem, the brushes, and need maintenance all the time. The brushes, not the whole motor. So that's the only problem, I think, for it, but it has good characteristics. So let's go back to the Yes. So that's general structure of DC machine, motor or generator. And sometimes the stator, they call it the yoke. It's the case outside protecting the doesn't matter. Okay, that's the pole. I want to you look at the pole. That's where in the stator when I showed you the first picture. Yes, did you see these 4 poles? These windings wrapped about around the poles. It look like that. They make it look like that. They call it the pole shoe. And it's laminated. Why laminated? We said that before when we studied magnetic field. Laminated because they want to avoid the eddy currents. Because we will have magnetic field, and magnetic field produce electric eddy current, which is circulating inside the core of the iron. So they make it like very thin pieces of metal to minimize the eddy current. And that's the pole where they have the wiring around it. And we'll do some calculation for this one, but this is the way that they put their field wind. Okay. That's the way they do the rotor, by the way. So they have the teeth, and then they put like 1,000 of them, but they are all insulated. Between this sheet and the second one, there's insulated material between them, not touch it. Why? Also for the eddy current. They have big current, they have many coils. And of course, there are the air holes here for ventilation. And they stick it together. That's where they put the wire, the coil. So if they have one coil here, that's the beginning. Go back and then just go on 180 degree, and then here you go. I bought one coil on the, of course, you got hundreds of coils in. Okay. How they connect the windings. But before we say how they connected, I want you to take care of some terminology used with any machine. You will hear the word turn. What is turn? Turn is like that. 2 conductors connected, we call it one turn. That's the turn. Has 2 conductors. Coil. Coil has several turns. Like if you have, this is one turn, second term, third term, and then you have that's what that one coil. So turn has many turns, and then if you have group of coils, you can connect in parallel or series and parallel. We call it wind. So when you hear because sometimes people, they do not distinguish between turns, coils, winding. No, there are differences between the 3 words. So the winding is formed by connecting several coils, and that's important how they connect. In DC motors, they do have 2 types of connection. Let me just run quickly for it. There is something called lap winding and wave winding. I'm not going through the details of these 2 winding, how they do it, because this is like technical work, but you got to know as engineer the difference between them. I know how to do both winding because I told you that in my bachelor degree, I'm in the German school, so they care about the technical too. So they got us motor, and we're making the lab winding, wave winding in the workshop. But all what I want you know, in lab winding, they connect the windings and the coils in series in parallel. In a way, they will have parallel path, as you see here, equal to the number of poles of the machine. What does it mean? I have here 4 parallel paths. It means this machine 4 poles. If you have 2 poles, you will have 2 parallel paths. What are these? What you find here, that's the winding. How they connect the coils parallel in series. In the end, they will have parallel path. The number of parallel path or the number of parallel path of the winding equal to the number of poles. So if you have 6 pole machine, you'll have 6 parallel lines. Well, what is the advantage of this? You can divide the current over many paths. So it means that this machine can operate with high current. So if they need application requires high current, high amps, they use the lap. They wind the motor in a way to have many parallel paths to divide the current over many paths here. So you will have high current machine, and of course the voltage will be low. The other kind of winding, wave winding, they have only two, whatever the number of poles. They don't care about the current, they care about the voltage. So this kind of machine, when it's operating with high voltage and low current. So that's mainly that I want you to understand. So we call A, let's call A the number of paths, that's here is equal P, where P stands for number of poles of the machine, and A here is equal to 2 in wave winding. What is A? Number parallel. Okay, that's what just before I. Okay, so we know now the terminology used with the DC machine. There is something also important between mechanical angle and electrical angle. Explain what's the difference between both angles. There's mechanical angle. Mechanical angle, we are familiar with it. Like if you have anything and make one cycle, one rotation, it makes 2 pi. That's mechanical. Electrical is not like that. To explain, let's assume that we have 4-pole machine, as you see, north, south, north, south. And let's say that this is the axis you are going to start to calculate the angle. Now, there is something important. That's the north. Let me make it bigger. North, the magnetic field coming out of it, right? So in this air gap, you will find that the magnetic field, and by the way, it's always concentrated at the center and getting weaker at the ends, right? So you'll find in the middle of the pole high intensity of the magnetic field, and every time you're getting away from the center, it's getting weaker, all right? Till even you come here, you'll find it's really very weak. So that's coming out. What about the south? The magnetic field going in. But of course, the concentration is really high in the middle and getting low at the edges. So it's in. And the north will be coming out, and the same thing, and then that's all. So what I'm saying here, I want to understand this graph, because I didn't get it when I was a student also. I have to struggle with it. So this theta, you start counting the angle 0. So that's the axis. That's y-axis, see? And obviously that's the first pole, the north, and coming out, so the direction is out. But you observe it's weak and increasing to come in the middle. In the middle, we'll find that almost constant. And then when you're getting away, so if I'd like to, if I say this point 0, all right, and this is point A, and that's in the middle point B, and this is point C, and that's D. So I can say this is 0, this is A, and in the middle B, and this is C, and this is D when you are gunning. So that's the way that, and why I'm making positive, because I assume that when the magnetic field coming out in the air gap, it's a positive. And then when you go to the south, it's going in, inside the pole itself, so it's changing the direction, and that's it. You have 4, and the north here finished 2 pi, and then have 2 pi. So, and then we'll go the north again, you will start another cycle. So as electric cycle, it's done here. As electric cycle, because they have north, you have south, and you're going to repeat again. So that's your cycle as electrical cycle, that's here. So what you observe that the electric angle is half the mechanical angle. So So here, the electric angle is equal what? That's example for 4 poles. So you divide 4 by 2, you get 2. That's why during one mechanical cycle or one rotation, you have only 2 electric cycles. That's the first cycle, the first electric one, and that's the second one, because you have 4 poles. So always to find the electric angle, you divide the number of poles by 2. Why divide by 2? Because one cycle, it's made by one north and one south. So, and every one north and one south, they make one cycle. That's one pair. North and south, they make only one pair. They make one electric cycle. So if you have, let's say you have 6 poles, 6 poles mean they are going to make 3 electric cycles. Oh, it's easy formula here that the electric angle, how do you calculate? You divide the number of poles by 2 and multiply it by the mechanical angle. So to make sure that you understand, let's if you have 6 poles, what does it mean? P is equal 6. So in one rotation, how many cycles will be done? Okay. Now the second question, what about if I say that the motor rotate by 120 degrees? That's the mechanical one. So what's the corresponding electric angle? 6/2, right? Times the mechanical angle, which is 120. So be 3 times 120 will be 360. So when it make 120, that will be 60. Okay. Now let's go for another thing. Pool pitch. What does it mean? As I explained that the magnetic field coming out or in, it depends on north and south, but I want to focus on the region where the magnetic field for each pole. So how they calculate that? They will say that if you go from the center of one and the center another pole, and you look at this distance, that will be considered as a pole pitch, which can be calculated easily if you know the circumference of the rotor. But you might ask, you have many circles. You have the stator, you have the rotor, right? That's another question keep in my mind. So if this is the stator, let me just make it, that's the stator. And you got inside the rotor, so that's the rotor. And that's outside the stator. In the magnetic field in the air gap, that's the effective one. So I go for here, in the middle gap in the middle, and that's the radius. Or I can take it here, but you don't exceed that, right? So that's how you can calculate the one pole, which is spread by 180-degree electric. There is something also called the coil pitch. That's also, if you have one coil, let me show you. It's the distance between one conductor and the second, because any coil, as I said, has 2 conductors. So the distance between them, that will be called the coil pitch. And now, if you hear the word, there are 2 types of motor that you can say that it's full pitch or short or fractional pitch. When can you say that or that? If the distance between this conductor and this conductor fill the whole pole pitch, so it's full. If this one is shorter, the distance between the first and second conductor of the coil itself, the size is less than the pole pitch, you call it fractional. It's just terminology used for usually armature winding, we use the full. But in EC, for some reason, we use the other one, the fractional one. Okay. Now we'll go for the important part. There are 2 things. Induced EMF in the DC machine and the torque produced. The induced EMF, it depends obviously on the magnetic field intensity. And it depends on the speed of the shaft and the size of the conductor, the number of turns, the number of poles. That all collect all these things in one constant, we call it Ka, and it's known as the machine constant or the armature constant. And that depends on the size of the machine itself. And here I got all details of this constant. The number of conductors. What's the number of conductors? We said each turn has 2 conductors, right? So to calculate the number of conductors, see how many windings do you have? How many windings? I have 100 windings. Okay. How many coils in each winding? I have 20. And there are 2 conductors in each turn. So you multiply the number of windings that you have by the number of coils by the number of turns that you do. So you get the total number of conductors. They are like conductor like that. This is 1 conductor. And this other conductor making the 1 turn. That's 2 conductors. You calculate all the number of conductors. So that's the total number of conductors. P, the number of poles. It's 4-pole machine, 2-poles machine, 6-pole, usually in pairs because you have multiple towers. And divided by 2 pi A. What's A small? I said A number. A is the number of parallel paths. It's going to be equal P if it's lap winding. It's equal 2 if it's wave winding. All right. So that's the constant of the machine. From this equation, obviously it depends on the size, right? On the size of the machine itself, the number of conductors, the dimension. What's phi? Phi is the flux per pole. Under each pole, what is the amount of flux? How can you calculate it? You should know the flux density under each pole and then multiply it by the area of the pole. So that's the pole. So, and you should find the area. How you find the area? All right. Let me so if that's the stator. Let's say that you have 4 poles. 4 poles, you have 1, 2, 2, 3. Of course, it should the distance should not be very huge. In any way, of course, it has a thickness or has a width. How can I do it right? It's like that. This is the region where is the area of the pole. Show that here. I will create here. So that will be the area. So if this is the radius r, if you found the whole thing, you will say 2 pi r. It will give you the circumference of the whole circle. And if you have 4 poles, you divide by 4, it will give you just the length of this one under 1 pole. If you have p pole, you divide it by p in general. So it will give you the length of the arc that's concerned with 1 pole, right? If we have 4 poles, you divide by 4. And then multiply it by L, the length or the width of this depth. It will give you the area of the pole. All right. But they give you a factor because the whole magnetic field covering this whole area that I divided, for example, by 4, maybe it will only 75%, and the weak will ignore it. So you can multiply by factor whatever it's given, but it's not given to you. Consider it ideal that you don't lose anything. So that's how you calculate the area under each pole. Okay, and omega m, it's the armature mechanical speed. That's why I put m here to make sure it's mechanical, because now we have 2 speeds, electrical, mechanical. That's the mechanical speed. So that's how you can calculate the induced EMF machine, generator or motor. What type? DC motor. So simply it depends on the magnetic field and the speed. Every time you increase the speed, the voltage increase. You increase the intensity of magnetic field, increase the voltage. And Ka is the constant. It's not in your hand. In your hand if you are designing the machine, but if you are buying the machine, you don't have control over the Ka. All right. If design it, if they want to have big machine with big induced EMF, they play in these things. Like if you want to have high voltage, you will have many conductors. You will have 1,000 turns instead of 500. You can double it by this. Now A is the number of parallel path. So how you do high voltage? You make A small. So which kind of winding? The wave, because it has only two. So that makes sense now. So that's how they can control the reduced voltage in the machine. Well, the variable reduce in the machine the torque, the mechanical variable torque. The torque, it depends on the magnetic field and the current. You don't observe that the two equations that I started with this lecture, it's the same, very similar to this one. You remember in the beginning of the lecture, I said the force depends on BLI and the voltage depends on BLV. It's just the same. If you go now to the machine, to this equation, that's instead of pi B, and actually B is calculated because B times A gives you the flux. Omega, it's the speed, but that's angular speed because the example I give it to you was moving in translation motion, straight lines, but now we have rotation. So instead of B, we have omega, and K is a constant. So it's the same thing. About the force, I told you the force is equal BLI. B is the magnetic field. You have the flux. You have the I. And L is the dimension. It's inside Ka. Then you will ask, Ka, you just mentioned Ka for the voltage, are both the same constant under one condition, that you are using omega. Then you say somebody else can, yes, some they like to use N. What's N? Revolution per minute. N is revolution per minute. That's another way for the speed. If you want to calculate, no, don't use N. If you want to use Ka for both, you have the same numerical values but different units. So it's better to use omega in both. So how we can find omega? Because usually when they write on the machine, they don't write omega. They write 2,000 RPM. So you should convert it to omega. How you convert it to omega? And by the way, mechanical. That's equal. Okay, let me remind you by electric one. Omega in electric, what's it? 2 by F, right? But F, it was cycle per second. Hertz, right? Cycle per second. Now you have N revolution per minute. So in second, you divide it by 60, right? So you have 2 by N over 60, which is equal pi N over 30. So to find the omega, the angular velocity of any machine you have, just multiply pi times N over 30. It gives you in radian per second. And in this way, the constant of the machine Ka, both are the same. Ka, I already explained, phi, we said that the flux, they're one pole, and the Ia is the current. Okay. The example now, I'm not planning for that, but I prefer something else. I hope that they have it with me here. Maybe I don't have. I have a video about it, so I can show you next time. So I will just leave you here to ask any question about the DC machine in general. We just explained the physics of it. So if you have any question. Yes.
What is Z again?
Z, total number of conductors. Total number of conductors. And remember, one turn has 2 conductors. This one turn has 2 conductors. So if you know the whole total number of turns, but usually you don't give you the total number of turns. They will tell you how many coils per winding and the number of windings, and then you can multiply and get it. but this is the total. Now that's why it's very important to know the terminology used. Turn, coil, wind. Yeah. So if you know the number of coils per winding, and you know the number of winding, multiply by 2, then you get the number. Yeah. Any question? Yes. All right. This is the, oh, you need the torque? All right, that's the torque. And just I will tell you about something else. The energy should be reserved. So if you look for the, if you want to calculate the power, what's the power? E times I, right? Volts and current. E times I. And the mechanical power, that's electric power. What's about mechanical power? Mechanical power is equal to torque times omega. Times omega. If you look for the torque times omega, what's torque? How do you find torque from this equation? K phi I, right? K phi I times omega. What's omega phi K? Yeah. I prove it from mechanical to electrical. And you can do the same thing. Electrical, go to mechanical. Yeah, same energy. Which? All right. Done.